that we are all invited to have lunch at 1 p.m. at Plaza Mayor. We have a cocktail there. We are all invited for those of you who have to eat. So we are all invited, okay? So at 1 o'clock. So we made it 1:30. Okay. So now I have the great pleasure to share this session of this small workshop. The session is on collaborative project, and the first one is going to be given by Juanjo Palacios, and I will serve this other as a novel platform for topological superconductivity. So, Juanjo?
Thank you. Thank you all for being here. Yeah, it's my pleasure to open this day talk, and of course I have to thank the board, the IFIMAC, current board, and the board, not only for organizing this meeting, but for
So, what about now?
Much better.
We have to stay here. Okay, I'll do my best. So I was saying that I have to thank not only the organization of this meeting, but also, of course, this initiative to come up with this collaborative projects. There are definitely, personally, I have benefited a lot from them, not only scientifically, but also professionally, because I had a chance to start collaborations with people that I otherwise have started those collaborations with. And also importantly, the amount of paperwork for this project is nearly zero. And this is something that I really appreciate. Get funding is so. I want to talk about this the current project that we have going on at this point. It started less than a year ago. Title is Disorder as a Novel Platform for Topological Activity. Actually, the ultimate goal of this project and the overarching goal of this project initially was something like we want to come up with a new platform for Majorana frameworks. Maybe the term Majorana framework has been used and abused quite a bit lately. So finally, when writing the project, we decided just to turn not sound bit and just talk about connectivity in very generic terms. And if at some point Majorana frameworks appear, yeah, that would be good. But anyway, so the main idea, the one you guys have to take home, is that we think that we can design, or we have found a new platform, a new hardware for topological superconductivity for Majorana frameworks in bismuth, in amorphous bismuth, or amorphous alloys of bismuth and antimony. The reason is basically because amorphous bismuth turns out to be superconductor, and bismuth and alloys of bismuth and antimony, they are topologically non-trivial. So we combine the two things, and we think that maybe we have the, like I said, hardware for Majorana framework, Majorana zero bounds. So maybe some of you, or most of you, are familiar with some of the terms, terminology in topology, topological materials. And typically, when you think of topological materials, you have in mind something like a band inversion, right? The bands are inverted. Or you think of computing like very connections, very phases, turn numbers, V2 number, which in the end is something makes use of the parity of the wave functions at time reversal invariant momenta, Wilson loops, this kind of things, right? Maybe at some point you have heard of some of the work on the area and you know these things. So basically, the way we classify topological materials is in momentum space, in perceptual space, using all this jargon that I just mentioned. So I wouldn't be surprised if you're surprised that I'm putting together in the same sentence amorphous and topological. And the reason is that we can also classify amorphous materials in terms of being trivial or non-trivial, pretty much the same way that we can classify crystalline perfect materials with the standard lattice. And this is just an example that I'm going to comment in a minute. This is just a model of a disorder two-dimensional lattice. And one of the manifestations of material being trivial usually is the presence of the protected edge states in two dimensions or surface states in two dimensions. And this is just an example, as you can see here. This is where the material has this edge state protected there. It happens to be at zero energy at the middle of the gap, as it should be. So yeah, amorphous materials can be topologically non-trivial. And this is part of the things that we are exploring from the theory. Part. So anyway, this is a collaborative project, and we have a team, and the team is formed by 3 other groups. The one led by Nicolás Agrait, the one led by Roberto Otero, and the one led by Isabel. The 3 of them are in the quantum physics department, as you probably all know. And let me just mention that this group, the definition of the group is kind of flexible, clear, and open. So in this case, Nicolás Agrait, who is an expert on glasses and other materials, and now he knows his way around. He knows his way around the amount. He's leading a collaboration with other people. In this particular case, Julia Gordillo at the department, some collaborators at the SMAM, Andres, is the Center of Natural Analysis for Materials, which is the city of the as you probably know. Gaston and some students, one of them, funded by this project. The second group is Herman and Isabel's group. As you know, they are well-known and recognized experts in the field of low temperature, high field physics. They have built an impressive lab with tons of really cool toys. They're actually cool and cold because you need to have these dimension refrigerators that can go down to 10 milli-K. You can read it, but 10 milli-K, and they can go up to peaks, multiples of up to 22, I think, the largest one. And they have built this in this floor, this vibration-free floor, so you can do actually careful detailed measurements of the things that we want. So their expertise is essential for this project because they know how to apply magnetic fields and measure vortices, superconductors, and kinds of things. But one thing that I want to stress is that they also have some expertise in the synthesis of materials, quantum materials, now we call it. And this is, I mean, a really important part of the project. They want to synthesize. So their group is PhD students, one of them funded by this project, and two postdoctoral students. And Roberto, I hope here. Sorry, Roberto, somehow I missed.
Never mind.
Picture.
My picture is there.
There was an image here with some this with the surface that Roberto had. I don't know if that's how. So yeah, Roberto, he comes from surface science, so he knows how to basically grow monolayers and few layers of materials, or any material. And he now has started this combination of STM measurements with the optical measurements using what is called localized plasma resonance. We might find useful along the way in this project, and also the experience in the positive materials, in particular ferromagnetic materials, is going to be important for this project at some point. And yeah, so this is down there. And this is me, of course. I resolved the equation essentially. And I'm defining group as just my closest collaborators at this point. In this case, it will be Alberto Cortico, Antonio Picon, our talent in department of chemistry, and the students that we have, in particular Antonio, I think, funded by this project. So anyway, why Majorana Premium? Why Majorana Remote? We're going to look at about these things. It's basically because there's a claim out there for the past few years. You can do topological quantum computation. You can build quantum gates out of them. And just a kind of cartoons or images to illustrate that. You can use Majorana Premiums that are presumably are located in vortices in a superconductor, the topological superconductor. In this case, the idea would be that if you have two of these Majorana Premiums, then these two are going to be forming a single charge fermion. So when you manage somehow to interchange the position of the two vortices, then you're going to create some angular state for the charge fermions by doing this. This was one of the initial proposals. We like entanglement to be able to do some computation, and some other proposal is, for instance, the combination of the quantum anomalous Hall insulator with the quantum anomalous insulator, and electrical measurements can actually give you some sort of like I said, gate on that you can play with. So anyway, this is just the excuse for what we are trying to do. The hardware in this case is the first idea for hardware in this topological superconductor business or business. It goes back to Juanjo. They propose, okay, we need to have induced superconductivity in a singly degenerate Fermi surface. Okay, it needs to be non-degenerate. In this case, a non-degenerate Fermi surface would be the one that you can find on the surface of the topological insulator. You know that we have electrons on the surface, and then if you induce superconductivity, standard superconductivity, as well superconductivity on these guys, then in principle you can pair these opposite K and opposite spin guys. I will say the simple way, but it can be done. Okay, so this singly degenerate Fermi surface with topology with the superconductivity induced in it is the main ingredient for that. You can have a two-dimensional Fermi surface, or you can have a one-dimensional Fermi surface. You can have a two-dimensional quantum spin Hall insulator or topological insulator. Then what you have is on the edges, you have chemical states, and the Fermi surface, the singly degenerate Fermi surface now is composed of only 2 points. But that's okay, it's going to be the same idea. So this is the main ingredient. And we need another ingredient, which is in order to locate or to localize the Majorana zero mode or the Majorana bound state, we need to break the universal symmetry, and then you can do it with ferromagnetic materials, or you can do it with magnetic field. And in this case, the prediction is that you can find Majorana zero mode at the core of the cortex of this topological superconductor. So the way to build a topological superconductor, as I said, you need superconductivity and singly degenerate Fermi surface. So what these guys propose is let's proximitize the topological insulator with the superconductor. So the superconductor we put on top of it, and then we reduce by proximity superconductivity to the topological insulator. And then in the vortex, we're going to find this guy. Something more interesting, at least to me, is the possibility of having intrinsic topological superconductors, which means the very material has all the properties it needs. For instance, in this case, this is a material made up of the iron and selenite and tellurium. We have a band inversion. Remember that the main ingredient to have topological non-trivial features is to have a band inversion. We have a band inversion at some point, but this is not an insulator. We have bands crossing the Fermi level. So these bands are the ones that develop superconductivity. At the same time, you have this topological non-trivial nature due to the inversion of these two bands. So in this material, we expect to have a Dirac cone of electrons on the surface, and at the same time, coexisting superconductivity. So I mean, I think it cannot get any better. Right? And yeah, they are claims in this paper where you just apply magnetic field, you get vortices, and if you look in the middle of the vortex, at the core of the vortex, you are going to find some zero energy state, which presumably attributed to the presence of the Majorana zero mode. So this is basically the idea. There are some other hardware. The most famous one is the one that was popularized by Leo Kammerhofen. 10 years ago, you proximitize a semiconductor, in this case in antimony, with a standard wave superconductor. And in this case, with due to the strong spin-orbit coupling that the semiconductor has, the magnetic field that you apply and the proximatization, remember that we need this impedance, magnetic field, superconductivity, and strong spin-orbit coupling. With this thing we can build, we can find the Majorana zero mode. Then they claim that some zero bias features that appear to be attributed to the Majorana zero mode. Over the years, people have been improving this technique, and they have been now creating nanowires that are surrounded by the superconductor. And these guys are better for a number of technical reasons, more magnetic fields or magnetic field, and whatever. So in principle, these things are having improved over the years. But you can read, probably you know, this is a very controversial topic. With things like that, when you go to science, then the editor is warning you, okay, guys, just we're publishing this, but be careful because people out there are questioning the validity of this result. So it's a controversial topic, not clear so far clear the status of this message. Some other possibilities, you can play with systems of junctions and you deposit the superconductor. You deposit the superconductor on top of the two-dimensional electron gas with the stability of coupling, and then you play with the phase, and then you can get, again, presumably you can get zero bias anomalies or zero bias features that are associated with the Majorana zero mode. Maybe the most popular one, or one of the, I would say, more clear hardware systems where these things can be observed is the ferromagnetic chains deposited on a superconductor. In this case, this would be the equivalent of some famous model which is called the theta F chain. The presence of the Majorana zero modes is associated with the formation of the band of these U-Shiva pushing off states that appear when you have superconductors with the magnetic moment there. And yeah, somehow those things combine to form these Majorana zero modes, which presumably again are at the end of this chain. And the IDD curves with SDN, you can see peaks at the end of the chain, nothing in the middle. So this is the kind of thing we are typically looking for. We are looking for some zero bias anomaly at the energy located somewhere. In particular case, at the end. So yeah, anyway, so with all this background, this is we have this idea. I mean, the whole thing is controversial, but we decided that we can continue to the field by introducing our proposal. The proposal for hardware is based on two observations. The first one is that, as I said in the beginning, bismuth antimony alloys are topologically non-trivial in many senses. If you for instance start with bismuth, pure bismuth, this is a trivial material, not so trivial because actually it's a higher order topological installation, which means that it doesn't have Dirac surface states, but it has Kinch states. Okay, one-dimensional Kinch states. This is the manifestation of the higher order topological. Okay, if you add a little bit of antimony, 7% of antimony, then this is the first example actually of the actual topological insulator in the literature. If you add antimony, then you get a system with a gap, a fully topological insulator. You have one inversion, and then you get, like I said, the first measure of topological insulator. If you keep increasing antimony concentration, then you end up with the topological semimetal, which means that you have Dirac states on the surface protected by topology, but there is no gap, so you have coexistence of the bulk states and surface states. But it still is topology in that sense. So as you can see, not so uncommon to have topology around. And second observation, this is the one that I think is more interesting, is that if you go back to the year I was born, these amorphous alloys are superconducting. Okay, so the typical temperature of these alloys, in this case, you can take a look at here. Alloys with antimony, you can get typical temperature up to 6 Kelvin. So yeah, you combine these two things, and then you might expect to have what we call superconductor. We have two scenarios. The best case scenario, the first one, would be, as I said, the combination of the amorphous material contains the topological material of the crystal. In this case, then we expect to have protected Dirac state, coexistence with the superconductivity of parts. Okay, this is the first scenario. And the second scenario is if we are not lucky with that, and this material doesn't topologically trivial, then we still have this possibility that if we can combine the crystalline phase with the amorphous phase in this way, then by proximity, if this guy is topologically trivial, but still superconducting, by proximity we can increase superconductivity on the crystal phase. And the crystal phase, whether it is just bismuth or bismuth antimony, or whatever is going to be topologically trivial, it's going to have surface states, it's going to have Kinch states, and you can have here for bismuth, etc. So maybe we can play the game of inducing by proximity superconductivity on the topological material. Okay? So conceptually, this is the most interesting case to me, but this one also might work, and this is part of the fun of this project. So how do we know that if this amorphous phase is a topolically non-trivial material? We don't know, because we cannot go to the standard catalogs that you can find out there. Maya Bernoulli and Frederick and collaborators, they have been creating these enormous catalogs of materials, stoichiometric materials, crystalline, and you can just go and look see if your material, the one you have in the lab, is topologically figured or not. And they have examined like thousands of them, and they have found that 3,000 are topological insulators, 4,000 can be topological semimetals. So I mean, at this point now we can just look it up. But of course, this is not possible for amorphous materials for non-stoichiometric materials. There's no catalog for that. So we have to do something about it. And the thing to do is we have done some theory. Initially, we are doing just some simple model at this point. We call it the Wilson Dirac lattice model. This is just a simple model that recreates the transition from trivial to non-trivial, from topological with topological insulators, etc., just on the basis of a single parameter, mass parameter. And then we have generalized this to introduce disorder. So basically, instead of just having a simple cubic lattice, we have a disorder lattice, a disorder model that is presented. How do we compute, how do we characterize the triviality or non-triviality of the amorphous material? Then, since we cannot make use of the standard techniques, we have to come up with something different. Actually, for some type of topological insulators, there are something called local markers. They are called Springbok index and some local churn index that can be used for disordered material. We can compute some quantity at the local level, not in the reciprocal space, but in the real space. But this can be done for time reversal invariant topological insulators. There's no such market out there in the community. So we decided to use what is called the entanglement entropy and entanglement spectrum. The idea is very simple. You have a system to split it into halves, and then you compute the reduced density matrix of one of the halves. This is something that actually I teach on the mechanics here to the guys. You can characterize this density matrix by the entanglement entropy, and then you know the degree of entanglement. You just compute this quantity to compute the entanglement spectrum. The entanglement spectrum is just you basically diagonalize the density matrix, compute it on half of the system. Okay? You diagonalize that matrix, this is non-interactive electrons, and then you obtain spectrum. The spectrum can be characterized if the system is translational invariant. You can have a case, the vector here, and plot things to give like a Wilson loop. But if not, we just have a spectrum. We just have a bunch of numbers there. Most of them are 0, most of them are 1, and some of them are in between 1 and 2 for this matrix. So we want to identify the non-triviality of the system in this aspect. Okay? So the way to do it is, okay, we need a secure way of computing or at least classifying this, and the secure way is based on the Wilson loop. We compute the Wilson loop, we can do it for the crystalline phase, and we know when a material is trivial or not, if it's still crystalline, we can keep it, and this is the reason to do it. But we can also do it for a small disorder. Okay, so for perfect systems, a small disorder will compute the we call the number, or we can say whether the system is trivial, topologically trivial or not. And then what we do is we just we don't want to be complicated of the spectrum. So what we do is we build a convolutional neural network. So we feed in the spectrum, and then we just computing the Wilson loop. We just say whether or not this spectrum below corresponds to a trivial case or to non-trivial case. And the important part of this, the important part of this is if we can classify even systems without we can classify systems that don't have a gap, and this is important because we cannot use the Wilson loop for systems without a gap. So we can predict whether an amorphous material is a topological insulator or not, even without the presence of a gap. These are just some examples that I don't have time to explain, but basically this is the figure that in the beginning. Amorphous materials can be topologically non-trivial, and we can actually predict it on the basis of entanglement spectrum. I don't have much time to go into details, so I'm going to just go and skip the experimental part. We're doing some more the theory part. And we want to build in practice discover materials, and we want to do it using implantation. We want to use the implantation beamline of the SMM by introducing the picture of the implantation line. And what we want to do is to disorder the samples that are grown by us, in this case, thin films or perfect crystals, grown by the lab or grown by Isabel. These are just some pictures of the films, same picture of the film. And This is a simulation of what we want to do. We have already started, but what we want to do is to, in this case, a simulation of the implantation of protons on thin films or crystals. And as you can see here, what we expect from the simulation, this one, is that we can create a design profile of vacancy implantation if you want to resolve it. You create in a controlled way on the sample. And this is somehow what we like. We want to have some strongly disordered bulk region underneath the surface, which is more or less crystalline in this case, in a controlled way. So this will correspond to the second scenario that I mentioned in the beginning. We have already some experiments, and we are trying to characterize the result. Still, we are not there. We haven't been able to find or create a lot of materials, but we are creating damage. So this is visible. We should be able to get there. This is just a big characterization. We can do that for thin films as well. This was the film numbers for bulk states. For thin films, we can do the same. At this point, we are in the process of characterizing things. We don't seem to be able to create amorphous or to reduce amorphization or taxation in films yet. So we have to learn how to do it. Within the process, these are some analyses that we are making. And finally, we are doing some resistivity measurements. We want to find superconductivity, hopefully. So we have started doing some resistivity measurements for pure visible disorder in this way, to implantation of vacancies with protons or with visible atoms, say. And we are not there yet. We have seen so far just a behavior, no traces of superconductivity there. And we have some hints in the magnetization that even pure alloys, they might have some transition in the form of filaments, superconducting filaments that are formed in the material. See, work in progress. Actually, as I said, we have been working on this for a year, so we still have a lot of work ahead of us. And hopefully, eventually, we will be able to measure the vortices. This is an example of the vortices of disordered material. So that means pretty done. And hopefully, we will find some signature of the zero energy mode in one of the vortices once we have the material going. And yeah, this is the picture that we're using. I don't know what appears here. The summary, yeah, amorphous visible or amorphous and thermally visible alloys. It looks like a very good platform for hardware for topological superconductivity or for Mariana zero modes or frames. Thank you. Thank you.
So we have time for questions or comments. Please. Probably you have you want to remark the main achievements of this project, which is the main result.
Well, it is ongoing project, so at this point we would like, on the experimental part, definitely we would like to be able to get an amorphous visible or visible and thermal alloy. And we want to actually achieve that in an alternative way, as I mentioned, using this implantation line. Because we don't want to do the standard way, because in the standard way, the amorphous alloys or these amorphous systems tend to recrystallize when you heat them up. So we try to find a way to stabilize the amorphous phase. Hopefully, from a full.
You have some ideas for that, the stabilization of the.
You can talk to okay. We have. And the theory part is also interesting because we definitely want to understand whether or not. I mean, first question we want to answer is this material actually topological superconductor, topological material? We are not there. What do you think?
Yes.
I work with light. I'm gonna ask.
Could you speak a little bit louder?
Yes, sir. I work with light, so I'm gonna ask. All right. Have you considered anything related with light matter interactions to destroy or create superconductivity in these topological systems, or especially related to these
not. The answer is no. We haven't thought about how to use light to use or to destroy it. I don't know if you can think about it. Why not? But the normal specific.
We might consider. The other thing that we were thinking is that depending on the kind of material that you deposit, in particular, if you create applications with plasmonic materials, plasmonic something, you might actually seek for some modifications of the plasmonic modes depending on whether underneath the material is the conductor. And we're thinking by in a relatively flexible way because it was not the main idea of the project.
So, yes.
How did you get the space in the vortices? It's possible to do that in such a way that you can get creative.
It's a lot funny. Can you get ready?
I think we should thank Juanjo.
Thank you.
The collaborative project, which is going to be presented by Nicolás Agrait.
No.
He's going to talk about charge and heat transport in atomic and molecular junctions. So, please, Nicolás.
Okay, this project is one of the old projects, so it's not one of the ongoing projects. But it's not there. So as we will see during the talk. Okay, here the idea is well to learn about charge and heat transport in atomic and molecular junctions and protein based. That was the idea of the project, and it was a collaboration between Rubén Pérez, Juan Carlos Cuevas, and myself. So two theoretical groups and one experimental group. Here the question is that, in fact, we really know a lot about charge transport in the nanoscale, in atoms and molecules, but heat is a much more difficult question. Also, in the case of more complicated molecules like proteins, well, things start being also very complicated. Okay, this project ended in 2019. So, well, we got very nice results with high impact. As you can see here, this is for the first objective. There were two objectives, basically. One was thermal transport in atomic scale junctions. And there were some very high impact publications. I want to remark also that we had one of the questions that was the difficult part for us was the development of a new setup for conductance measurements, for thermal conductance measurements, because, okay, let's say the measuring a charge current is easy, but measuring a heat current is really very good. So in this case, so for the other objective, we had transport through biomolecular junctions. There were also some nice theoretical results. We also tried some STM measurements in some proteins and also some conductance measurements and thermopower measurements in amino acid junctions. So in this well, I must say that in this project that was collaborative, well, the collaboration was not so intense as we would have liked, because, well, in fact, the problem was on our part, on the experimental
was much more difficult than we originally thought to develop a setup to measure thermal conductance. So, well, we kept working. I mean, we have been working on this goal for a long time. And I would say that the project is not dead because now we have a new project with Juan Carlos and myself that is aiming at measuring heat transport of thermal electricity or electricity part in single molecule reactions. So now we have really developed the system. It took many years, many more than we thought, to develop a system able to measure conductance in this very small system. So since it's always nicer to talk about ongoing things in the future than the past, I will tell you about our setup for measuring thermal conductance and how it was. So basically, what we want to measure is the heat current when you have say, outside and outside. If this were just an electron current, it would be easy. We can put devices to do that, like an ammeter to measure the current, but there is no such a thing for heat current. We have experience in measuring this kind of thing. For example, in this case, we could measure the thermal power in atomic contact. This was in collaboration, in the previous collaboration with Juan Carlos also. So we could measure the thermal power in one atom contacts, and we have experience measuring the thermal power in molecules. But measuring the thermal power is relatively easy because you are still measuring currents. You keep one side and then measure the current of the voltage that is induced by this temperature difference. Okay. So this is the same in the case of single molecules. You can also measure, say, the conductance and the thermal power. This is the simultaneous measurement of conductance and thermal power in a C60, for example. This is the conductance and this is thermal power as we form the junction. So in that sense, that is something that we know how to do and that is relatively easy to do. And well, it gives an interesting insight into the transport properties of molecules. Okay, going back to measuring the thermal conductance in a one atom contact, there are not many groups that can do that. In fact, there are only 3 in the world. And the question here is that the setups that they use for that are quite complicated and it require a lot of engineering to form these platforms. This is basically a calorimetric bit. You have a heating resistor here. And so the idea is that you can measure as you form the contact, you could have a change in temperature in this platform, and that is what you measure. And so that you deduce what is the heat current. But building such a thing is, well, it's quite complicated. And well, we had the idea that we could do simpler and cheaper also. In fact, this is the group that was collaborating with Carlos. Okay, another group uses, well, a similar idea. Instead of having the calorimeter, this is the IBM group. Instead of having the calorimeter on the thing is on the substrate, but in this case also this is, we want our sensor to be able to scan with the function of an SCM. And if you have something like this is very difficult because this platform is very soft, so you cannot really scan your sample. Okay, so we really like this approach. Well, the same group, the Michigan group, also measured the thermal conductance in molecules. Just in one case, in this case, the resolution that you need is, for example, you can see that to measure a molecule, you need to have a resolution of 80 picowatts, which is a very small number. In the case, say for the atoms, you can do better. I mean, you can have you don't need such a small resolution with 500 picowatts. So these heat amounts are very, very tiny. Another approach that is used by a group in Germany, that is in detail, is to do a micro pipette thermocouple and use it as a tip. And they were we're able also to measure different things in thermal transport and also atomic contacts. In this case, the resolution is about 4 nanowatts. Okay, so our idea to try to get a simpler setup to measure this, or something that we could implement in our lab, was to use, well, there are 2 possibilities. You can use a hot wire. Basically, you heat a wire, so instead of having a platform, you have a wire where you pass a current, and then from the changes in the temperature of the wire that you measuring the resistivity, you can deduce what heat flow you have. Another approach, and very easy here, is to use 2 thermocouples, 2 Wollaston wires, very thin wires, say 5 microns or 2 microns in diameter, and solder them at the end and use them as a tip. So you can measure using the thermoelectric properties, you can measure the temperature. But the resolution of these systems is not very good. Well, anybody will tell you that it's not a good idea to use hot wire, if you think about it, to measure, say, something as small as an atomic contact, because you don't have enough thermal resolution. It can be too soft. It is very difficult to calibrate because you need a very precise modeling. The thermal properties change and are not reliable, the data that you can get from them. So you really need to do a very precise calibration. And also it's difficult to get if you have a hot wire, the temperature at the tip. You can also have contamination, and so it's really a bad idea. But anyway, we decided to go this way. So to solve these problems, we found that we could, we devised a new method of measuring using, measuring the resistance, but also the thermoelectric temperature of the wire. So we were measuring several signals at the same time. And in this case, this has several advantages that we will see. We can use this, you can see here the 2 Wollaston wires soldered at the end. This is the tip. And you can get from the thermoelectric properties, you can get the temperature right there. So you know what temperature you have, just measuring the DC voltage that develops between the 2 wires. We can put this wire as a tip and scan with it, as you will see. To measure, we need to use several different frequencies because we want to measure many things at the same time. Here, for example, we want to measure the average temperature of the wire, so the changes in resistance that will give us so measuring here, we will get the average temperature of the wire. We measure also the temperature of the tip by the thermoelectric thermocouple that we have there. And we also measure the tunneling current going to the substrate. So we can use it as an STM. Okay. Of course, to do this is necessary to avoid having leakage of the heating current into the sample. In this case, we use an AC heating current, and that way we can use a locking detection to detect very sensitively the changes in resistance of the wire. Then we can demodulate the signal at the different frequencies. We use a different frequency for the tunneling current, and in DC we get the tip temperature. So we are getting these 3 things all the time. Okay, well, one interesting thing, and when we started doing this sensor, is that if you look at the equations of this, basically we said that you need to model them if you want to, in the end, to get the temperatures and everything. But we realized that just by looking at the things, you have different factors here that intervene in the heating of the wire. For example, here you have the blue heating that takes place along the whole wire, but you also have this thermoelectric term here that is acting only at the junction. So we have here local or heating or cooling that takes place right here. This is essential in our system because in this way, you can do all the calculations for the system, how it heats up and everything. But then what you find is that you have this local source of heating or cooling here that is very useful because you can use it for calibration. Basically, what we do is we measure the changes in resistance of the wire. For example, this is well, a simulation of what happens with the temperature of, say, half the wire. This is the central part of the wire. If you have if you make a contact, then the temperature will be reduced, so you will get the red line, basically. So although the change in temperature is very small, it's typically of the order of millikelvin, we are working at those temperatures, but still we need to have a solution for a wire of less than a millikelvin. It seems small, but it is possible. Okay, so here we can use, we can calculate the resolution of a wire to see what we would get. So theoretically, basically we can measure in the AC signal, we are measuring the changes in resistance, and we have a resolution of 5 volts per watt. For the DC, the thermocouple signal, we have a resolution of 3 volts per watt. But it is easier to measure the AC signal because it is AC and you can use lock-in and demodulate at a high frequency. So we are getting enough resolution to measure an atomic contact. So we need to have basically 125 nanovolts, which is something that we can. Okay, well, this is the, before I was considering the other solution I was showing, it was a simple model, just a simplified model to calculate and obtain an analytical formula for the resolution of the wire, but you can do it, say, considering that you have 2 different metals. For example, typically what we have is platinum on one side, one of the wires, and the other one is platinum rhodium. And then you will get an asymmetric heating. So, for example, if you have platinum, it will be the red parabola. Well, it's not a parabola because when you put everything, it's say a sharpened parabola. It's not exactly a parabola. But when you have 2 different wires, the temperature is asymmetric. But well, it doesn't matter because what you are measuring is the average temperature. That's what we care about. You are also measuring the temperature right at the middle. Not the hottest temperature, but right at the junction, where that is where you are making the contact, which means that you know what temperature you have there. So with this, say for our water, we will get, say, if we solve the equations, but including say everything, we will get like 9 volts per watt. That will mean that, okay, we have enough resolution. We need to measure a 1 atom contact. We need to measure about 0.5 nanovolts per watt. So the one interesting thing about this kind of sensor is that you can use these thermoelectric properties at the junction to provide a local source of heating that you can use for the calibration. So that is, remember that we had an AC current going through the wire that is heating the wire, and we are measuring the changes in resistance or the changes in temperature, but we can add other currents at different frequencies. And they will be, I mean, we can measure them independently. So for example, if we add a DC current to the AC current, then that will, on one side, provide a joule heating for the whole wire, but it will also, say by the Peltier effect, it will cool or heat the junction locally where the 2 wires are welded. Okay, so we can use this as a very precise calibration for the wire because we are, instead of having, say, the losses when we make the contact, we can use for the calibration this DC current that we introduce in the system. So in this case, we don't really need to model the wire, so it's not necessary because we know exactly how much heat is being dissipated or absorbed in the thermoelectric junction. Okay, and what changes in the average resistance that produces. So this is you can see this here. For example, if you have the red curve is what happens when you do a DC ramp. So you have the new heating provides what gives you the shape of a parabola. We are measuring here the changes in resistance of the wire, or the changes in voltage of the whole wire. And then you can see that there is a cooling in the first part, so it goes below zero because you have this Peltier effect. And then if you increase the current, then the heating takes over, and you get still the heating. But this is, you can, if you put an AC current of the same values, then you can see that the parabola is exactly the same. So we can account really very exactly for the Joule heating and separate it from the Peltier cooling or heating. So for that, we know the amount, I mean, by this shift in the two parabolas, we know exactly the amount of heat that we are putting into the junction and the changes in resistance that we are seeing in the whole wire. Thereby we can find the resolution. For example, in this case, this is an experimental case, the resolution is 7.2 volts per watt. In this case, when you increase the temperature, it's 9.2 volts per watt. Okay, so we don't need to do any modeling. This is really a very serious advantage because not measuring is really very complicated. So one important thing to take into account as everybody working with local probes know is the stiffness of the probe. If you want to be able to do an image with the probe and to scan and make contact and everything, your probe has to be rigid enough so that you can do it. In this case, our stiffness is 1.4 kilos per meter, vertical one, and we are able to scan and see steps and make contact. So that is enough. Okay, we are approaching, say, this direction, and this stiffness is the lateral stiffness. Okay, so let's see what happens when you try to measure. In this case, we go to the real experiment when you want to measure anatomic contact. And so we make here we are far away from contact. We start approaching the sample. The zero is when we make electrical contact with the sample, but you can see that so this in this plot here we are plotting the thermal conductance that we are observing. So we are far away, well, like more than 10 nanometers away. We have no thermal conductance into the tip of the sample. We are separate enough. Okay, there is some radiation, but we are not seeing that because that is smaller. And then what we see is that around 7 nanometers, we find some conductance. This is before electrical contact. Okay, so, well, there is something on the sample, of course, before we make the contact. So probably there are some absorbates and we have cleaned the sample, but this is not in ultra high vacuum. It's in high vacuum, but not ultra high vacuum. And the sample has not been cleaned, say, by spatuling or anything like that. So we have a layer of something, of some absorbates that is about 7 nanometers thick. Okay, we can now retract, and what we see is that, okay, this red curve here, this is the part where we are in contact, and we can see from the part where we have the metallic contact. So here we can plot the thermal conductance as a function of the electrical conductance, and we see that, but from the slope of this curve, we get that we have like 1.2 nanowatts per Kelvin per atom per quantum. This is like double of what we would have, but we should have, because basically we have this contribution to this absorbate layer. Okay, so we were happy with this result, but still. Okay, if we go to smaller contacts and trying to do some local cleaning, but say heating locally the tip to a higher temperature and then crushing the tip and scanning and do some wild things, then what we find is that we can really get rid of that layer, at least for some time, this absorbate layer. And here you can see this is in a different scale. This is well, less than 2 nanometers from the sample surface. You can see here that the thermal signal starts almost right at the spot where you have the electrical current. Okay, there's maybe a little something this line PVC is for 0.4 microwatts. Okay. When we retract, well, we get this curve because now the temperatures have changed. Okay, we have to take the typical thing that we see for atomic contact. And in this case, from the slope, if we measure the slope in the metallic contact area, what we can see is that we get the conductance of one thing. We don't have, we succeeded in getting rid of that actual data. Well, I think it's one. Okay, one thing, we still have a problem. It is that, for example, if we do what we were seeing is that it was difficult in the experiments to get a contact of one atom, just a one atom contact. We know how to do that. For example, here you can see what with this sensor we can get here. This is the one atom contact here. This is the two, so it is quite clear. We get a conductance of 1 G0. But when we have the heating current, which is an AC current, we get a similar curve, but we don't see the steps. So the steps get blurred by this current. So we thought, well, maybe it's, everything gets heated up and then we lose resolution. But it is not that, because if we heat with an AC with a DC current, then we still see the steps, right? So we found out that the problem is the magnetic field. Well, the remaining magnetic field in the system, probably also the Earth magnetic field, because we are using a relatively high, several milliamps current to heat the tip. So that would be enough to provide some lateral motion to the tip due to the magnetic field. It is small, just half a nanometer or something like that, but that would be enough to prevent us from seeing the contact. So we are working on that to compensate that problem. So let me see, a lot of people have participated in this system, but most of the work, or the biggest part of the work, is done by Gwen. Yes. One thing is that with this new setup, we will be able to really measure the conductance of contacts and molecules, and continue with this collaborative project.
Yes.
I'm glad to give the right talk. So you mentioned at the beginning of your talk that you also want to measure the activity of proteins. So I'm surprised. Why
Yeah.
did you measure the activity of proteins?
Yeah, well, we did some measurements in everything with STM, basically. But it was very difficult to, well, the results were difficult to interpret. In fact, it's difficult to know what you have in your junction. So probably using an AFM would be a better idea if you have a conducting AFM. I mean, we really wanted to measure also the thermal power. The measurements were not very good.
And you support that proteins are not linked for conductive current.
Yeah, but
Can I say something?
yeah.
The problem is that for certain proteins, like actually the mechanism of conductance is still under debate. Some people say it's copy, some people say it's tunneling, and that's why it's interesting. That's why.
Yeah, Linda participated in the collaborative project, the previous one.
Mr. Will?
Yeah, you kind of have to leave it. So you calculate the frequency. So you
I know how to.
you should have also thermal node.
Yeah.
And it will be mainly related to the resonance frequency. Did you see?
Well, the point is that we have what we have checked is we haven't checked it, and we don't know what the amplitude should be. But what we have seen is that if we keep the chip to the same temperature, but with a DC current, we have good steps in the conductors, which means that it is related to the AC question. So we are trying to solve the problem with the magnetic fields, but we will check that to see. It doesn't seem to be the problem.
No, I mean, I don't.
Yeah, no.
It's a problem. I'm
No, but it would be a problem. If it's oscillating, and for us, it would be a problem.
Yes, Nicholas, you mentioned Peltier effect. Usually Peltier effect, you get cooling from contact between semiconductors. So I was surprised to see that mentioned this metal, basically. And second, the question, what is the heat sink here? Where your heat flows, in the wire or surroundings?
Yeah.
Well, to the first question, you're right. I said Peltier heating in the junction, but it's not fully correct. It's this term. This term here, the green term is not. This green term here is not really the Peltier cooling. It's Peltier and Thomson. It's a mixture of both. So the Thomson term comes from this change in seabed, but it is combined. I mean, it is the equation you see that it's combined. So it's Peltier Thomson.
Okay. And where this heat flows?
Yeah, the heat
is
flows
in one of the wires? Or?
Yeah, no, the heat flows say from both wires. So this part is the hottest part, is the central part. So the heat will flow from this spot, the central welding, to the sample. So it will be flowing through the one atom of the molecule.
But to the sample, you have basically only single contact flow. So this is the idea to estimate positive and negative heat which goes to the sample.
Yeah, so right.
Last question, Emma?
Yeah, I wonder about the frequency dependent of your AC. I mean, you probably have 10 kilohertz bandwidth or something like that.
Yeah, something like that. So for the heating, I mean, the thing here is that we want to use an AC heating, but it's at a high frequency. We were using about 20 kilohertz. In fact, because we just want to heat. But we want to heat above the response frequency of the wire because we don't want an oscillating temperature there. We want a constant temperature. So we are using AC because it is easier to detect. And it provides us freedom also to measure the DC part.
And you go above the bandwidth of your field.
Well, for the and we compensate. So here the voltage due to this heating is zero, basically. So we check at that frequency if there is current leaking to the sample. And for the tunneling bias, we use a lower frequency like 5 kilohertz.
Okay. Thank you very much, Nicolás, and thanks. Module 9.